Okay. Well, good afternoon. And my name is Shattur Shide. I am a PhD scholar at IIT Bombay. I work on machine design, electric machine design, and this is the 11th week doubt clearing class of the NPTEL course Electrical Machine 1. So today the focus will be on tests and series motors. But last class there was one question on 4-point starter. Shashidhar asked the question. He is not here as of now. So the question was why at all 4-point starters are used, or say 3-point starters are already there. Then why 4-point starter was a necessity? We'll look at it. We'll start with it. Then we will move ahead. Okay. So left hand side here what we have is the 3-point starter. Right? Why 3-point? Because there are 3 points: this line, field, and armature. 3 points are there. Now we told that this solenoid or this inductor, this electromagnet, this is the uh, no voltage release coil, no voltage release coil, or under voltage release coil. What happens is, when the machine is running with full voltage, then this plunger is in this position. This iron pole that gets attached here, if I draw the iron pole, it gets attached here and it stays there, and the machine runs with the zero series resistance with armature. But the thing is, uh, last class we talked about the speed control of DC motor, and we saw that if you want to keep the speed or take the speed beyond um, the rated speed, obviously at reduced torque, then what we have to do is we have to weaken the field. So to weaken the field, say in the F we have the field winding connected. To weaken the field, what we have to do is to increase, we have to increase the field resistance, series field resistance. That will reduce the field current and the machine speed will increase. But the problem is this under voltage solenoid, the current that this solenoid is carrying, if you see this coil is in series with the field winding. So if the field current reduces, this coil will also carry the reduced current, and as a result the attraction force of this electromagnetic, or of this electromagnet, that reduces. And if you keep on reducing the field strength, at some point it will release the plunger. This plunger that came here will be released because of reduced uh, electromagnetic pull, because there is a spring that is pulling this handle back towards this side. So with a 3-point starter we cannot do a considerable amount of field weakening. After certain field weakening, the machine will stop, because this uh, plunger will be released and the machine will go to the off position here. Is it clear up to this? Why we cannot do much of field weakening with 3-point starter? Looks like. So we cannot let the field current flow through the no voltage release coil. If we do, we cannot do field weakening. So the current through the no voltage release coil must be given a separate path. To do that, this 4-point starter was introduced. If you look at the 4-point starter, there are 4 points. One point is here, line, other one is here. Okay, we will look at it later. We will see what are common with 4-point and 3-point starters. Okay, F, field, and A. These 3 points were there in 3-point starter also. The new one is this. This no voltage release coil current is now flowing through this point to the neutral or the negative DC bus. So basically the no voltage release coil current is now no longer flowing through the field. Now you can do as much field weakening as you want, and that will not affect the machine operation. So is it clear up to this? Why 4-point starter is advantageous? This is a 4-point starter. Okay, so if you have no question, I think series motor has been discussed in today's earlier class. I will mostly talk about tests in this lecture. So two kind of tests of DC machine has been discussed. One is the no load test, which is also called as the Swinburne's test, and the other one, which is very interesting, at least to me, which is Hopkinson's test. We will first look at the Swinburne test. Swinburne test is a very easy test for a DC machine. There are two objectives of Swinburne test. The first objective is to estimate armature resistance. The other objective is to estimate the B. What is B? This B is not the magnetic field B. I will write the equation. Torque, electromagnetic torque equals J d omega dt plus B omega plus load torque. So whatever electromagnetic torque is developed, it has three components. So as you can understand, as the steady state reaches, this component becomes 0. So at steady state, the electromagnetic torque supplies the load torque, as well as it opposes, not only opposes, it counters and the frictional loss, friction and windage. Windage loss means the loss due to, or the counter torque due to the viscosity of air. And if it is a water submerged or some other, then the whatever fluid is there. So basically this B, or in other word, how much viscous drag or friction drag is there against the rotor, that much we have to estimate with this test. That we can do with this test. So two tests we can do, two things we can estimate out of it. All right. So how to do Swinburne test? So as I mentioned, that it is just a no load test of DC machine. This is the armature resistance Ra, and say if you have a starting arrangement like this, we talked about starting procedure of DC motor in last class. You have a starting procedure like this, and in this way you start the machine. Just a second, আমার কিন্তু ক্যামেরা অন আছে। Okay, in this way you start the machine and then run the machine at no load. What do we need to measure? We have to measure the current and the voltage here, right? Now see, if we draw the equivalent circuit of the machine, under no load, this is the terminal voltage, and this is the back EMF E. This is the back EMF E. This is the resistance Ra and some current I is flowing, right? The first thing is we have to find out the resistance R. Now the current that we measured from with the ammeter is V terminal minus E by RA. Back EMF we cannot measure. So here we have two unknowns. One unknown is the back EMF, other unknown is RA. So we need another method to find out the RA, armature resistance. One way is to do the block rotor test. Block rotor test means you simply block the rotor, make sure that the rotor does not rotate. The rotor does not rotate, and you give a very small voltage to the rotor or to the armature, whatever. If you give very small voltage, why very small voltage? We discussed last day that armature resistance is very small, so you cannot give full voltage to a standstill motor. If you give a very small voltage, maybe you can do it up to the rated current also. Very small voltage will give rise to rated current, and you can find out RA like this. Once you get RA from it, you can find out from this equation the back EMF E, right? Now E is known to us. E is known to us. Now if you see here, this current that is flowing, it is flowing against this back EMF E. So we can think as if this current is, say for example, if you have a battery like this, and a current is flowing across the battery from positive to negative terminal. So basically this current is charging this battery, right? Similarly here also there is some electrical circuit element, and a current is flowing from its positive to negative terminal, means power is being absorbed. So power being absorbed by the armature is nothing but back EMF times I. This much of power is being absorbed by the armature. Now the machine is running at no load. The machine is not supplying any load power. Then where is this power going? This whole power is nothing but the frictional loss. Is nothing but the frictional loss. So once you know the frictional loss, which is B omega squared, right? Frictional torque, if frictional torque is B omega, torque into omega is speed, so frictional loss is B omega squared. You measure the RPM of the machine, and from there you can find out the B. So in this way you can find out what is the friction coefficient of this whole system. This is not only for the motor. Sometime you might have a motor connected to its load. So whatever B value, whatever J value you get, that is for the whole system, not only for the motor. So once you know the two parameters, one is the armature resistance Ra, and other one the friction coefficient B, then you can find out the efficiency of the motor under any loading condition. You start with any loading condition, then so in loading conditions, so for example, you take the machine, now you load it, say some load is there, then you measure the current with the ammeter. Now once you have the current I, you can find out the I squared R loss in the armature. You can find out the B omega squared loss, mechanical loss, so that is the loss of the machine, and of the machine, and rest of it goes to the output power. So you can find out the efficiency out of it. That's all about Swinburne's test. Okay, we will talk about Hopkinson test here. Hopkinson test. So if you have attended the transformer classes of this course, there was one topic that was called What was that called? Short circuit test. Back to back test of transformers. There was a name I forgot. Back to back test of transformer, also called as Sampner test. So the Sampner's test, the basic idea behind it was that we have two large transformers and we have to do hit and run test of the transformer. Means when the transformers operate at full load, how much is the temperature rise and all. But the transformers are of very high power rating in the range of megawatt and all. So you cannot keep on dissipating megawatt level of power hours after hours. So to do that, two different transformers are used, and one transformer is used to এই ফোনটা ধরো না and one transformer is used to load the other transformer. In case of Hopkinson test also the same thing is done. In Hopkinson test, two identical shunt DC machines are taken. Two identical shunt DC machines are taken, right? Now suppose I have two DC machines like this. Okay, now these two DC machines are coupled in both electrical and mechanical manner. Means their shafts are coupled like this, and in electrically also they are connected. Okay, now one machine acts as a motor. Say this is my motor. Other machine acts as a generator. So what is happening? The motor is providing mechanical power to the generator through the coupling, and the generator using this mechanical power is generating electrical power, which it is feeding back to the motor, right? So the motor running the generator is running the motor, energy is flowing in between them. Now if these two machines were ideal machines, that is there was if there was no there was no loss in these machines, then this would have kept on going infinitely, one machine feeding the other, right? Energy conservation law is not violated at all. But the thing is, they are not ideal. They have their own losses. So they can keep on doing this, but at some time they will stop. So there need to be some arrangement from outside. There need to be some arrangement from outside which will supply only the loss of the two machines. So 2 times the loss will be supplied from outside. So suppose these machines are say 50 kilowatt machines. Okay, both of them are, let us say, 90% efficient, right? So if you have 50 kilowatt machines with 90% efficiency, without Sampner test, if you do not do Sampner test, just simply full load the machines and test, what you have is you will be drawing from the how much, sorry, input times 0, okay, 50 by 0.9. So this much of power you will be drawing from the supply if you do not do Sampner, sorry, this Hopkinson test. 50 by 0.9, around 55. Okay, 10% is the loss. So 55 kilowatt of power you are drawing from the source to test one machine. But if you are doing the Hopkinson test, all you are drawing is 2 times 5, that is around 10 kilowatt of power from the source, and you are testing two 50 kilowatt machines together. Only the loss is drawn from the source. Is it clear? two machines, one running the other, motor running the generator, generator running the motor, and they're drawing only the loss from the supply. Okay, so now it is understandable how the circuit will look like. Okay, let us see how experiments are done in laboratories. Okay, so if you do this Hopkinson test experiment in your university laboratory, first once you reach there, you will see there are two motors, not motors, two machines. Uh, there are two machines which are mechanically coupled. Two machines which are mechanically coupled. Okay, identical machines. Now you have to make the electrical connection also. You have to make the electrical connection also, but not right now. You can join the neutrals, but here you have to keep a switch. We will see why. Then there is the, not like this, there is the DC source of the laboratory, and the DC source is connected here. DC source is connected here, like this. You also have field of this machine and the field of the other machine. These field currents are controllable. Okay, there can be starters also here, or series resistances to start the machine. Okay, now we are starting the machine. Once you start the, give the supply, what will happen? This motor, we'll call it motor 1 and machine 1, not motor, machine 1, machine 2. This machine 1 starts running as a motor, right? Machine 1 starts running as a motor. Machine 1 is now generating, machine 2 is generating some voltage. Now you have to have a voltmeter here across the switch. What you have to do, so first what we do is, first we start the machine. Secondly, the field current is adjusted so that voltage, this voltmeter rating is 0. Because if the voltmeter rating is not voltmeter reading is not 0, then these two machines are just two different voltage sources, and we cannot short circuit them like that, right? We cannot short circuit two different DC voltage sources. We can short circuit only if their voltages are same. So what we have to do is, we have to adjust the field currents such that their voltages are same. Okay, so once the voltages are same, then we can close this switch. So once this is ensured, switch is closed. So once you close the switch, you see two voltage sources, say 10 volt here, 10 volt here, shorted like this. In this condition, there is no current through the circuit. So this is called the floating condition. There is no energy transfer, neither from machine 1 to machine 2 nor from machine 2 to machine 1. Now suppose you want the machine 2 to be a generator. So you want the power, electrical power, to flow from this side to this side. To do that, the back EMF EB of machine 2 should be more than the back EMF of machine 1. How to do that? We know that back EMF is K phi omega. Now omega is same for both the machines since they are mechanically coupled. K is same for both the machines since they are identical machines. So phi, we will now increase the field current in generator 2, sorry, in motion machine 2. Once we increase the field current, then what happens is its EMF increases. So in series here, there is the armature resistance. Here is the armature resistance. Once you increase the field current, then back EMF EB2 becomes more than EB1, and whatever the difference is, that divided by 2 RA, that much current flows from the generator to the motor, right? So right now what is happening is the generator is feeding electrical power to the motor, and the motor is running the generator, that is feeding mechanical power to the generator. So this is the basic setup of Hopkinson test. After that you will have ammeters here. So whatever voltage you have here times this current will give you the loss into 2. So this product, whatever VI product you get, that divided by 2 is the loss of every machine, total loss, and other parameters can be calculated out of it. So is the concept clear? Okay. So that's all about Swinburne's test and Hopkinson test. We will discuss one problem today. No, where is it? And that we will conclude after this problem. Next week, I am planning to solve one problem on Hopkinson test. Okay, we have one big question and 4 sub question for it. Let us read the question. Okay, DC series motor has half ohm of resistance, and it is driving a fan at 800 rpm while drawing 25 ampere current from a 200 volt DC supply. Now DC series motor means the field is in series with the armature. So whatever resistance 0.5 ohm is given, that is the combined series resistance of the armature and the field. One more thing that has been mentioned here is a fan load. A fan load can be the ceiling fan, a fan load can be a pump is also a fan load, a fan load can be a turbine, okay, means turbine of a ship. So what happens in fan load, but it didn't mention here, yes, the torque is proportional to omega square. The torque speed characteristic looks like this. Torque is proportional to omega squared. You keep increasing the speed of the fan, the torque required also keeps on increasing. So basically if you look at power power becomes proportional to omega cube. Okay, so the machine was drawing a 25 ampere current from 200 volt supply and running a fan at 800 rpm. The load torque is, we have to change the speed of the motor to 900 rpm by controlling the supply voltage. So the speed of the motor will increase. Yesterday, means in last class, we discussed a problem where a constant torque load was given. We discussed that hoist or elevator is a constant torque load. Here we have a fan load. The torque is not a constant torque. The load is not a constant torque load. So when we will change the voltage of the machine so as to get higher speed, the torque requirement will also increase. The fan is connected somewhere here, the fan load. Okay, the first question is estimate the required supply voltage in volt assuming linear magnetic circuit. So what has happened is that the speed of the machine has increased, means torque has also increased. So we have to first uh, see what is the torque equation. Torque equation is K phi Ia, right, for any DC machine. Now for a series machine, the field current Ia is same, sorry, the armature current Ia is same as the field current, or in other words, the phi is proportional to Ia. So we can write K times K1, some other constant, phi is K1 Ia, K1 Ia squared, or torque is proportional to Ia squared. Is it clear up to this? And the speed E, sorry, back EMF E is proportional to K phi omega. Okay. Can you help me after this how to start? We have to find out the required supply voltage. So to find out the required supply voltage, you have to first find out the current, right? So when there was 25 ampere of current, it was running the fan at 800 rpm, right? So we can write that torque 1 by torque 2 equals I1 squared by I2 squared equals omega 1 squared by omega 2 squared. Can I write this? We have used these equations, this equation and this equation. Torque is proportional to omega squared as well as proportional to I. So from here we can write I1 by I2 is equal to omega 1 by omega 2. So I1 was given 25 ampere, I2 we have to find out. Omega 1 was 800 rpm and omega 2 is 900. From here can we find out I2? 25 times 9 by 8, 25 times 9 by 8, 28.125 ampere. So this much of current is now required, but at increased voltage. Obviously we will see the voltage. So the second question is done, I think. Estimate the current that will be drawn by the motor after applying the above voltage. So this is done, 25 ampere. Sorry, not 25, 28.125. This is done. What is the supply voltage? So in the first case, there was 200 volt supply. So we had 200 volt supply here, 0.5 ampere, and sorry, 0.5 ohm, 25 ampere. So what are we trying to find out is we have to try to find out the back EMF E for the first case. E1 is 200 minus 25 times 0.5, 200, right? Yes. So it is 200 minus 12 and a half, so 288, 287.5 volt. So when the back EMF was 287.5 volt, the speed was 800 rpm. So when the speed is 900 rpm, what is the back EMF? Back EMF 287.5 times 9 by 8, 323.44 volt. So this is our E2. We have been asked to find out the supply voltage. So this was the case 1 before increasing the speed. This is case 2 after increasing the speed. So after increasing the speed, we have the supply voltage 323.44 volt, 0.5 ohm, and the current entering was this much of current. So what is the terminal voltage? Terminal voltage is simply KVL. It is 323.44 plus 0.5 times 323.44 plus 0.5 times 28.125, 337 volt. You can check the calculations later whether I am doing it correct or not, but this is the process. Okay, let me check it once again. Okay, I hope it's correct. All right. Okay, the first two questions are done. Now look at the third question. Estimate the required supply voltage in V in volt, assuming completely saturated magnetic circuit. So what do they mean by completely saturated magnetic circuit? Why at all this question is coming here? So if this is the BH curve, it's like this. So if you see, say at this point, BH curve is nothing but the psi I curve, same. So if you see at this point, say if you increase the H by this much, the B increases by large value. But in the saturation region, if you increase H by the same value, B increases very small, very little. So in saturation, what happens? Even with a large increment in the current, the flux in the magnetic circuit does not increase much because it is saturated. Now the question says required supply voltage assuming completely saturated magnetic circuit. See, they are saying completely saturated magnetic. Completely means what? Although this never happens practically, but for the sake of this problem, means like this, like this. No, this might happen if you go for a large saturation. This might happen. So completely saturated means even with increasing H, even with increasing current, the flux is no more increasing. It is constant. It has become constant. So the trick is when in the DC series machine problem they say that assuming completely saturated magnetic circuit, it means if I draw the machine once again, the armature is drawing a current IA, same current is flowing through the field. Now even if the armature draws more current, the field is also now carrying more current, but that is not reflected in the field force, field strength. The machine field is constant, or in other words, flux phi has now become a constant. With increasing current, phi is not increasing. So torque is now proportional to current. Torque was k phi ia. Now phi is a constant, k is a constant, so torque is proportional to ia, and it was proportional to omega squared also. So what we can write now is I1 by I2. Okay, what is the question? Question is the same. We have to increase the supply voltage so that the machine runs at 900 rpm, but now it is saturated. What is the new voltage and current? So I1 by I2 is now omega 1 squared by omega 2 squared. So it is 8 squared, uh, 8 squared by 9 squared. So what is I1 by I2? 25 by I2 is 64 by 81. So we have I2 equals 25 times 81 by 64, which comes out to be 31.64 ampere. So you see it is 31.64 ampere now. Previously, to run the machine at the same speed, run the fan load at the same speed, the required current was 28 ampere. So with increasing saturation of the system, we need more current. More current in saturated system, the current is more. It is very practical. So once we know the new current, I think our fourth question is done then. Estimate the current in ampere that will be drawn by the motor after applying the above required voltages. Sorry, 31.64 ampere. We have got it here. Estimate the required supply voltage in V, assuming completely saturated magnetic circuit. So we have already found out our E1, that was here, 287 for 800 rpm, and we found out that E2 was for 900 rpm, it was 323.44 volt. You notice here one thing, that back EMF E is k phi, sorry, k phi omega. K is constant, flux has become practically constant. So this we can directly find out from here, the back EMF. So we have to back EMF we can find, no, back EMF will change. Just a second, did I make any mistake? Okay. So the new back EMF we can find from here. Sorry, we got it from here. The new terminal voltage you can find out 323 volt and 0.5 ohm. New current is 31 ampere. So the terminal voltage VT will be times 0 0.5 15 C plus 8 3. This much will be the new voltage required. So any doubt about it? Okay, so I thought I will discuss one last thing. Okay, the torque speed characteristic, if you go through the equations of a DC series machine, the torque speed characteristic is like this of a DC series machine. So what we have is this rectangular hyperbola characteristic. So at very light load, the DC series motor tends to achieve a very large speed. So a DC series machine, a DC series machine can never run in no load. There has to be some minimum load on the DC series machine, otherwise it will take a very large speed. That is why this another question that is asked very much. Suppose you have a DC machine here, as DC series machine here, and you have a load here, some load here, and they are connected through a belt. They're connected through a belt. Now if something happens, this belt material might get hot and melted or something. This belt might snap. If the belt snaps, then this series machine starts running at no load, and as a result, oh sorry, I drew them wrong. This is the torque. So running at no load means torque is very small. The other way also correct. Anyway, torque is very small, and very small torque means very large speed. So if the belt snaps, the machine will start running at dangerously high speed. This is why DC series machines are never connected to load by belt. They are always directly coupled. This is the motor, this is the load. They are directly coupled like this. They are never connected through belt. If this is the connection, then there is no chance of this like the chance is very less compared to a belt snapping, that this machine will suddenly start running at no load. That is why DC series machines are never connected to the load through a belt. There is a very important question, very many times it's asked many places. Okay, so any question, or else we will stop for today. Okay, thank you for joining then. Bye bye.